Most of the metal lathes usually come with a so-called leadscrew. This is basically a threaded spindle going alongside the machine bed and allowing the carriage to move automatically when engaged with the half nut. The lead screw is directly connected to the machine spindle via a set of gears. These gears are called change gears, as they are supposed to be changed to get different ratios and therefore different speeds at the lead screw spindle. On bigger machines, the lead screw is exclusively used for cutting threads, as it provides a very accurate movement of the lathe carriage in relation to the machine spindle. To determine the right ratio, there are tables on the machine showing you which combination of gears to use for which thread pitch. There is usually a set of change gears coming with the machine, which allows you to cut all of the common thread sizes. However, cutting threads with a lathe is a very specific task which you might need from time to time, but more often you just want to have a power feed which moves your tool automatically to create smooth and uniform surfaces on your workpiece. For this, bigger machines have an extra feed screw spindle, but on small machines like mine, we just have to use the lead screw for the power feed as well. That means that compared to thread cutting, where the lead screw turns relatively fast in relation to the machine spindle, for the power feed it has to turn relatively slow. There is a set of two 20 and 80 teeth gears coming with the machine, which purposes a high reduction for the power feed. But even with these gears installed, the tool moves relatively fast. For roughing and fast material removal, this might be okay, but you sometimes want a finer feed rate to get better surface finishes. So my first idea was to install an extra motor to have a fully adjustable power feed. I bought this 12-volt motor, which turns at a maximum RPM of 100, and made this adapter to connect it to the machine's lead screw. Of course, an electronic lead screw with a stepper motor and controller would be the ultimate thing, but I'm just not ready yet for something like this. Instead, I have plannings about a complicated feed gearbox in mind, but we see if this ever comes to life. So the first tests with this new motor were very disappointing. As soon as I engaged the half nut, the motor stopped immediately. It seems that the motor just doesn't have enough power for this task. I bought this motor without any information about its torque, so I don't really know which torque range is needed to move the carriage under load. Instead of buying and trying out different motors in the hope of finally finding one which is strong enough, I decided to try it first if it is possible to rearrange the existing change gears in such a way that the result is a slower feed rate. So I took a look in the box with the change gears and found a 55 and a 30 teeth gear, which I stacked together as an additional reduction stage for the gear train. Now it was just a matter of fiddling around with a new set of gears, trying to find a position where all of the gears fit in the available space. I placed the new reduction stage on top and the two 80 to 20 gears behind. And to my surprise, I found out that the center of the 80-20 gear happens to be almost exactly above the already existing mounting slot underneath. If this is right, I just have to make an additional gear axle and a second gear bushing. Oh, and an extension piece for the lead screw is needed too. Because of the additional reduction stage, the gear train gets wider. But I'm optimistic that with these small modifications we again can add some value to the machine. So first we make the second mounting stud for the additional gears. I used a piece of 16mm C45 tool steel for this. And that's the finished part. It just needs a long set screw screwed in from behind to complete it. Next part is the bushing for the new gears. I decided to make the bushing out of brass instead of steel like the original ones, but I'm pretty confident that this is strong enough. The bushing needs a 3mm key seat, which has to be done on the milling machine. And last but not least, we need the extension for the lead screw. I made this from a piece of 12mm ground steel bar. There is again a key seat needed. And that's how the extension should look like in the end. I decided to solder the keys on both parts permanently into place. For the bushing I went with soft soldering, and yes, it was a drama. I'm really not that experienced in soldering, but no worries, it gets even worse when trying to silver solder the other part. But after several attempts and excessive cleaning afterwards, the two parts came out quite okay. Before installing the new parts, I will first measure the feed rate with the original gear reduction for comparison. So let's take a dial indicator. Nah, that's a little bit small. Oh yes, that's better. I marked the 0 position on the machine spindle so that it's easier to count one full revolution. With the original 80-20 change gears installed, I'm getting a feed rate of about 9/100ths of a millimeter per revolution of the machine spindle. And now it's time to install the new components for the additional reduction stage. First, the lead screw extension piece. Next, the additional mounting stud for the big gear. And finally the new bushing for the 80-20 teeth gear combination. It's a bit tricky to install all the gears and arrange them in a way that they mesh correctly, but after a few times it's doable. Let's see what feed rate we have now. One revolution of the machine spindle results in a feed rate of about 4.5 hundredths of a millimeter. That means that we now have about half the feed rate in comparison to the original gear train. In addition to that, I bought a third 20 teeth gear, which will give me the option of an even higher gear reduction, resulting in an even slower feed rate when needed. This smaller gear now allows for a combination with a 60 teeth gear, which will be the highest possible reduction without further modification to the machine. With this gear combination installed, the resulting feed rate is about 3/100ths of a millimeter per revolution of the machine spindle, which is about 1/3 of the original feed rate. In the end, I turned a test sample out of tool steel with all of the 3 different feed rates. On this sample piece, from right to left, it goes from slow to fast. It's not that easy to see the difference between the feed rates, but you can feel it when you scratch it with your fingernail. All in all, I think that's a good addition to the machine. I hope you found that interesting. Thanks for watching, and till next.